All right, excellent.
Okay. McMahon Labs Autonomous Vehicles, presented by Ishan Goyal, Devin Punevelu, Mihir Rao, and Truman Yu. What are autonomous vehicles? Oh, next slide. What are autonomous vehicles? Autonomous vehicles are vehicles able to function with the need of human involvement. More specifically, it is able to drive without the need of a human passenger, carefully paying attention to its moves. It is able to conduct the same activities as an experienced driver. The benefits of autonomous vehicles are that AV can achieve greater road safety, reduce congestion, resulting in less environmental gains and more productivity. The diagram provided by Synopsys displays the levels of automation in cars. Level 0 is no automation. And an example is the older cars with stick shift driving. Level 1 is driver assistance. Level 2 is partial automation. An example is if you do not turn on your indicator and you veer off the lane, the car will jerk the steering wheel back. Level 3 is conditional automation, and level 4 is high automation. Finally, level 5 is full automation, and an example is Tesla's ability to park by itself. How do autonomous vehicles work? Autonomous vehicles operate using a comprehensive array of sensors and actuators in relation with algorithms and robust processing units. These sensors are employed to detect the various signals from the vehicle's surroundings. The data gathered is then used to plot a course that effectively navigates around any detected obstacles. The vehicle employs several strategies. One such strategy involves the use of hard-coded rules. This is a straightforward approach where the vehicle simply maneuvers around detected obstacles, such as pedestrians. Another more advanced strategy that could be implemented is predictive modeling. This technique allows the vehicle to anticipate the future positions of surrounding obstacles, thereby enabling it to plan its route more effectively. This predictive capability enhances the vehicle's ability to navigate complex environments safely and efficiently. Project description. Autonomous driving has been a growing field in the car and technology industry, and when used properly, can be the safer and more efficient choice to dependent driving. Our objective is to identify the best machine learning method to train autonomous vehicles and thus achieve greater car safety. To compare the machine learning model performance, we built a miniature car using Raspberry Pi and various sensors modeled an autonomous vehicle as well as a maze and obstacles. The machine learning method that leads to the car completing the maze the fastest will be identified as the more efficient and accurate one. Now, Devin will go over the methods.
All right, so how do we plan to go about this? So as mentioned before, we'll be building two different types of learning algorithms, and we will use those to guide the autonomous vehicle through the path. We want to determine which type of machine learning algorithm would be best at creating the most efficient path with the least number of obstacles hit. The way we intend to measure our success is through a path we build on our own with various different procedures. We will run multiple trials with each type of machine learning algorithm. Then we will measure the time it takes for each of the trials. The time will technically be enough to measure the success of the algorithm. However, we want to take accuracy into account, so we will include obstacles throughout the path. For every obstacle that the vehicle hits, we will add a few seconds to the final time in order to reduce the success based on its accuracy. We will finalize all the trials and take the average and standard deviation for each algorithm in order to compare which one is the best. All right, so building our autonomous vehicle. So these are a couple of the materials that we've used throughout our project so far. So we have our brain, our main component, which in this case we use as a Raspberry Pi 4. For our motor-based functions, such as going forward, backward, and direction, turning left and right, we're using a motor controller in order to control the wheels. And along with a webcam that I'll talk about in a second, we're planning to use the Python OpenCV library to process images and video to make decisions. All right.
Why? I can just eat it.
So a couple more materials. So the chassis is an RC truck that we basically used because of its, it gives us enough space to put the rest of our components and wiring. So it's pretty spacious, and that's why we decided to use an RC truck. For a camera, we chose a webcam that will be used for various images, to capture various images of top lights, street signs, and road lines as well. And we also have ultrasonic sensors in the front and sides of our vehicle in order to detect the distance from obstacles and other objects. And then lastly, we have our maze. So this is the maze that we had mentioned before to test the accuracy and success of each algorithms. We have multiple different obstacles and paths on here that'll allow us to measure the success and accuracy of the algorithms. All right, now we're going to go to talk about training the autonomous vehicle.
So, as I mentioned previously, we will use two main methods to train the autonomous vehicle in its quest for achieving the best time. So the first method is supervised learning. So supervised learning is basically a machine learning technique that trains on labeled data, which is basically data that is already defined by predetermined characteristics. So in the model to the right, the shapes are already labeled by their types on the left, which leads the code to organize all the shapes depending on their types, as seen with the labels there. And in our instance, our input data are the images of the maze. So the car is driven around and the output will be how the car reacts to its surroundings. So how it accelerates or how it should turn if it needs to. So first, to collect the input data before testing, the car is driven through the maze using a remote control to allow learning, and the images are taken with corresponding values, which are necessary for data processing. Then the car will make decisions based on these data when the car is actually driving autonomously. So the second method is deep reinforcement learning. So in deep reinforcement learning, the model would learn by trial and error systems. So a reward system is established to incentivize learning. So it punishes or rewards the model based on the decisions undertaken. So an example of this will be our Atari Breakout, which is a game which involves breaking all the blocks at the top of the screen using a bouncing ball. And this will use a reward system, either you lose the level or you move on. So a reinforcement learning agent is initialized in our case, along with the environment, after getting the current state of the environment, and action is taken before the new state and reward are taken into account. Finally, the experience will be stored for future learning. The agent's policy is updated according to this experience. So the data is collected by moving the autonomous car through the maze, but this time by itself. When the car clears the maze, the training will finish and will be adjusted as mentioned previously for accuracy. Next slide. So finally, the end goal of this project will be to compare these two different methods, supervised and deep reinforcement learning. So the finished results will be compared to see which model best fits this specific situation with the RC car. So we will give around 10 to 20 attempts to find the average of all the times, also adjusting. And also we will find the standard deviation as mentioned previously, which can help determine the variance and how extreme certain time values are and where that can actually affect the final results of this project. So after all of these things are considered and taken into account, we can, in the end, see which model is better in our situation for this maze navigation. And now we will talk about future plans.
Okay, so immediately, our future plans include testing the deep reinforcement learning models and the supervised learning models, and training the deep reinforcement learning models to input values like turn angles into a data set for supervised learning in order for it to navigate the maze. Secondly, for the hardware side, we need to add a lighter power bank to the car while supplying sufficient power in order for it to run properly. Next slide, please. Plans for expanding this project include modifying this for more real-world applications, such as using more algorithms like imitation learning, which is currently being used by Tesla, our main competitors, as our advisor said, Dr. McMahon. Imitation learning mimics a human expert, in this case, a driver, in order to complete its task. Another method we can improve upon our project is increasing the safety of our autonomous vehicle by making it follow driving laws and adding road and weather conditions. On the right is a pie chart showing the main causes of a driving-related accident. By adding these scenarios in our experiment, we can maximize the safety of our autonomous vehicle. Next slide. We would like to thank Dr. McMahon for our advisor, and we would like to thank Professor Downing for supervising us in the lab. We would also like to thank ASDRP for this amazing opportunity. Any questions?